By now, you should be familiar with the capabilities of both Creo Parametric and Mathcad Prime. Let's see how we can leverage the combination of the two tools to help us with engineering tasks. We will use an example from the automotive industry. For this example, let's say I'm a systems engineer at a car company. In my current project, I am working with the mechanical engineers on the transmission team and also some outside contractors who are doing the CAD and drafting work. The contractors have come up with an assembly in Creo Parametric of the power transmission shaft. The mechanical engineers are performing calculations in Mathcad to ensure that the transmission can deliver the specified power without bending or shearing. Let's take a look at this assembly in Creo Parametric. For the ease of visualization, we have removed some of the gears on the shafts so we can focus on just one gear pairing. As you can see in this assembly, we have the input shaft on the bottom driving the output shaft on the top, which is in turn driving the differential on the right. In this particular gear, the driving gear has a radius of 23.5 millimeters, and the driven gear has a radius of 65.76 millimeters. We want the shaft to be able to deliver 250 horsepower of power while spinning at 2000 RPMs. We can put up some annotations to see the measurements we are dealing with. What you cannot currently see is that the input and output shafts are hollow. Let's use a cutaway view to look at the cross-section of the shafts along the length. The input shaft currently has a wall thickness of 7 millimeters and change. You might ask yourself, how was this number generated? To answer that question, I talked to the mechanical engineers on the transmission team, and they tell me that a series of calculations were made to determine the wall thickness of the shafts. They use Mathcad for their calculations. Here's the Mathcad worksheet that they created for this particular analysis. The worksheet starts off with the title page. It contains formatted header and footer information that is consistent with the company's standard template. The second page jumps right into the problem setup. I have a gear on the input shaft driving a gear on the output shaft. Scrolling down further, we see the geometric definitions along with the speed and power that I am driving the input shaft with. By doing a force and moment balance, we can calculate the amount of shear and bending acting on the input shaft. These values affect how thick the shaft walls have to be in order to accommodate the bending and torsion. If I need to change any of the input parameters, I can repopulate this worksheet with the new values and have it generate a new wall thickness. As the systems engineer, I want to make sure that the dimensions specified in the CAD assembly matches up with the underlying analyses performed by the mechanical engineers. As new requirements come in, the CAD parts and assemblies will have to be updated. They might affect the shaft dimensions, or it might not. Similarly, the mechanical engineering team uses Mathcad for all sorts of calculations, only some of which relate to the transmission shaft and its dimensions. Keeping track of requirements and verifying that they are met can be done by integrating Mathcad and Creo. As I scroll down to the end of this worksheet, I have a summary of the parameters that might be of interest to me. In this case, I need to know the power and speed that I'm analyzing, as well as the ratio of the input to output gears. I use Mathcad to run some calculations and come up with how thick the input shaft wall thickness needs to be in order to accommodate the bending and torsion. I can also pull out the torque and speed values on the output shaft as a reference. To tie the Mathcad worksheet to Creo, let's go back into Creo. We will switch over to a view that allows us to see the shaft dimensions more clearly. Now we add a Mathcad Prime analysis. I specify the worksheet and then the variables that I'm interested in linking. First, I pick the Creo parameters that I want to input to Mathcad. In this case, I am interested in the input power, the speed, and the radii of the two gears. We'll call them drive gear and driven gear. Next, I select the Mathcad results that I want to transfer back into Creo. In this case, I care about the inner diameter of the shaft. I will also pull the torque and speed values on the output shaft as a reference. I can now add this analysis feature right into the Creo assembly. We will name this feature Mathcad Analysis. I have already defined some relationships linking the parameters of the Mathcad Analysis feature to the dimensions in the Creo parts. This way, as new Mathcad values come in, the parts will update appropriately. Currently, the input shaft has an inner diameter of 7 millimeters and change to accommodate the 250 horsepower that's coming in. Take a quick mental picture of the input shaft dimensions as we will be changing it very shortly. Let's bump up the incoming power to 400 horsepower. I do this by modifying a Creo parameter. All I need to do now is regenerate the model, which automatically calls out Mathcad in the background. It comes back with a new wall thickness of 21 millimeters and change. And you can see that Creo has updated the inner shaft dimensions accordingly. If I want to perform the same analysis for a different set of gears, I can easily pick different gear radii and let Mathcad compute the wall thickness for that particular scenario. Or suppose I have a different transmission system that I want to repeat this exercise with. I can easily couple that system with the same Mathcad worksheet and perform the same analyses. Let's summarize this demo by seeing how it fits in with the PTC process landscape. The process landscape shows product development and various points of views that are relevant. Product development is a set of highly cross-functional and distributed processes that span the life of the product, from planning through support. We will focus on the engineering processes. The transmission shaft demo we just walked through shows off some of these business processes. First, concept development. Creo was useful in visualizing conceptual designs that you were considering. When used along with Mathcad, we can run studies and trade-off analyses to help us determine the feasibility of our designs. In system design, Creo and Mathcad are clearly very effective products for various engineers across an organization. As the systems engineer on this project, the value of integrating the two allows me to verify that requirements are met in an automated and efficient manner. In detailed design, we can take advantage of PTC's suite of multidisciplinary products to design and manage electrical and mechanical data. In our example, we were only interested in the mechanical portion. PTC offers tools to help you verify other requirements, like the software in the car's ECU. Mathcad can be used to analyze components in various domains and even be extended to standardized calculations throughout the organization. Under V&V, or verification and validation, we have already spoken about using Mathcad to verify requirements. What we didn't talk about was using Creo and Mathcad in conjunction with PTC's PLM solution to not only manage data, but also trace requirements. Finally, under variant design and generation, Creo provides a platform that allows you to design and manage modular products. Mathcad can also be used to analyze modular components. In our demo, we explain how we can easily change parameters in the Mathcad worksheet to drive a geometry change when there's a new or modified design. I hope you now see the value of integrating the capabilities of Creo and Mathcad, and how that works into your organization's engineering processes. Whether it be sizing the shaft for the transmission in your car, designing a cell phone case, an I-beam in a building, or air brakes in a missile, PTC desktop tools can help you in your day-to-day work.